Today we're going to solve some two-step equations. First, we're going to start by evaluating an expression, 5x minus 3. We're going to evaluate this expression for x is equal to 4. That means that wherever there's an x, we substitute in a 4. So we have 5 times 4 minus 3, and that equals 20 minus 3, which is equal to 17. We've just evaluated the expression 5x minus 3 for x is equal to 4. Now, let's try solving an actual equation. Three x minus 2 is equal to 10. What we want to know is what is x. To find that out, we have to get x by itself. So, we have an x that is being multiplied by the coefficient 3. We also have the constant 2, which is being taken away from the term 3x. We want to actually solve this in reverse order of operations. In other words, we do the addition and subtraction first. We do the multiplication and division after that. So, think of it as kind of peeling away the layers of an onion. We work from the outside in. What's closest to the x gets done last. So, we're going to employ the property of equality, in this case the addition property of equality. We're going to add 2 to both sides of the equation, so the equation is not altered. The balance of the equation stays the same. And we're going to get that 2 away from the x, the minus 2. So this goes away because this cancels out. The negative 2 and the positive 2 turn into 0. And on the right-hand side, we get 12. On the left-hand side, we get 3x. 3x is equal to 12. Well, we could probably solve this by inspection now. We know that x is equal to 4, because 3 times 4 is equal to 12. We know our multiplication tables. It helps a lot. But just to show the process, we know that the 3 is being multiplied against the x, so we use the inverse operation of division to get that 3 away from the x. Now x is by itself in all its glory, because the 3 over 3 just turns into 1, so x is equal to 12 over 3, which is equal to 4. Hey, we're done. We did it. Okay, what shall we do next? Now in this last problem, our coefficient of the x was positive. Do the same rules apply when the coefficient is negative? Let's see. Let's take the equation 15 is equal to negative 6x plus 3. Okay, as before, we want to get rid of what's farthest away from the x, what's most removed from it, and we want to do the addition subtraction first. So we're going to subtract 3 from both sides to get that constant away, and so 15 minus 3 is 12, and the plus 3 and minus 3 balance out, turns that value into 0. So we have 12 is equal to negative 6x. So now we divide by the coefficient of the x, which is negative 6. And we do the same thing on the other side, division property of equality. So we get negative 2 is equal to x. Let's check our answer, because that's always a good idea, by plugging the x back into the original equation. So we get 15 is equal to negative 6 times negative 2, which is what we decided x was, plus 3. 15 is equal to negative 6 times negative 2 is positive 12 plus 3. Does 15 equal 12 plus 3? It does. We're good. We did it right. We are happy. Moving on. What other kinds of problems might we see to solve when we're solving two-step equations? Let's try something a little different. I do have to find a way to erase faster. Maybe once I start using this program more, I will find a way to just wipe the screen. But for now, it just takes a minute. And my next problem, I am going to do 12 is equal to 8x minus 9. So I'm going to add 9 to both sides, getting 21 on this side and 8x on the other side. Now, I can tell by looking at this that I am not going to get an integer answer. Not a positive number, not a positive integer, or a negative integer. But sometimes that happens. So, the same rules apply. Let's just do this. I'm going to divide by 8 to get the x by itself. And so the 8 over 8 turns into 1. And x is going to equal 21 over 8. If I want to, I can change 21 over 8 into, let's see here, not 1, but 2 and 5/8 because 16/8 is equal to 2. So this is basically 16/8 plus 5/8. So it's going to be 2 and 5/8. But really, the answer 21/8 is perfectly adequate because in Algebra 1, we allow the use of improper fractions. As a matter of fact, they're quite useful sometimes. So, anyway, as you can see, it's perfectly okay to get an answer that is not an integer. And everything still works the same. What if we have numbers in our problem that are not integers? Is that any different? What would possibly be changing? How would we do a problem with fractions? And we could do decimals as well as fractions. But let's just for the present do fractions. So we're going to do 1/4 of a is minus 2/3 is equal to 3/8. Now what? Well, I'm going to add 2/3 to get it away from the a, and the minus 2/3 then balances with the positive 2/3, and it goes away, and I'm going to add 2/3 on the other side because I want my equation to stay balanced. So I get 1/4 a is equal to 3/8 plus 2/3. Well, I can't add 3/8 and 2/3, so I'm going to have to change both of these expressions, or both of these terms, to a common denominator. So I think I'm going to change them to 24ths. Makes sense. So I'm going to multiply this by 3 over 3. I'm going to multiply the 2/3 by 8 over 8. And that gives me 9/24 plus, let's put an equal sign there to make things not confusing, plus 16/24. So rewriting, I have 1/4 a is equal to 25/24. Now, a still needs to be by itself. And I could divide, since it's being multiplied by 1/4, I could divide by 1/4, or since it's a fraction, I could multiply by its reciprocal, which is 4. And so now I have to multiply the other side by 4 in order to keep things balanced. So I end up with A is equal to 25 times 4 over 24, which simplifies to 25 over 6, which is equal to 4 and 1/6 if you're a person who likes your mixed numbers and prefers those to improper fractions. But as I said before, there's nothing wrong with having an improper fraction in algebra. Okay, so now we've seen that we can do these kinds of problems and not get pretty integer answers. And we can even do these problems and not even have integers in the problems, and they still work. The same rules apply, the same processes, even if we're not working with integers. We're working with more complicated numbers. So, let's try a word problem. Everybody loves a good word problem because it represents math in real life. Let's say you're considering joining an athletic club, a wonderful place you can go to play basketball or volleyball with your friends, or swim, or work out on the weight machine. A great place for recreation. And you have two choices. Choice number one is you can pay $1,200 and you can be a member for life. But that's a lot of money, and you're not entirely sure if you're going to have the self-discipline to keep showing up, or maybe you might even move next year and you're not really positive that, it's going to be worth your while. How long do you have to continue enjoying your new athletic club to make it a better deal for you to pay the $1,200 than the other alternative? The other alternative is $100 entry fee plus $35 per month. Okay, let's compare the two and see how many months you would have to be a member at this price before you would end up paying more than $1,200. So let's, and $100 plus 35. Let's make the variable m, just to make it clear that we're talking about months. So I'm now going to subtract $100. You know what, I can kind of forget writing the dollar sign for a little while because it's just something extra I don't need to do. And I've got 1,100 on this side, and I've got 35. Oops, if I'm not going to do the dollar sign here, might as well not do the dollar sign there. So 35m. Now it looks like I'm going to have to separate the 35 from the m by division. So I'm going to do it over here too. So it looks like I'm going to have a division problem that is 1,100 divided by 35. Okay, 35 won't go into 11, but 35 will go into 110. I think it will go 3 times. 3 times 5 is 15, carry the 1, 3 times 3 is 9, plus 1 is 10, and now I end up with 5, and bring down the 0. 35 will go into 50 once. I'm going to have some amount left over, so I end up with 15. And so basically I know that in 31 months, I'm almost going to have paid $1,200. In 32 months, I will have paid $1,200 and then some. So I will go over $1,200 at 32 months. So what does that mean? What is 32 months? 24 months is equal to 2 years. So 32 months is equal to 2 years, 8 months. So 8 out of 12, so that's 2 years and 2/3. So if I think I'm likely to want to be at the gym, at the athletic club, for at least 2 years, 8 months, and enjoy it and continue to get use out of it, then I might as well plunk down my $1,200 and join right now. But if I'm the kind of person who likes to try things out and doesn't always stick with things, or I'm not sure if I'm still going to be in the area within the next year or two, then I might not want to plunk down $1,200, and I might want to just pay the $100 plus the $35 per month, because that way I'm not buying something that I'm not going to really use. So in this way, I can use math to make a decision about something I want to purchase that's kind of a major purchase, and I can make better financial decisions by evaluating all the information. Yay, math!